Hello everyone, welcome back. In this video, we're going to introduce the limits at infinity, and these limits will describe the behavior of a function for very large positive values of x and for very large negative values of x. These limits will allow us to define horizontal asymptotes, and we will be looking at methods of calculating these types of limits. So if a function is defined on an interval from a to infinity, then we write the limit of f of x as x approaches infinity to be equal to L if we can make the function arbitrarily close to L by taking x sufficiently large. Similarly, if a function is defined from negative infinity to a, then we write the limit of f of x as x approaches negative infinity to be equal to L if we can make our function arbitrarily close to L by taking x sufficiently large negative. Now, the line y equals L is called a horizontal asymptote of the curve y equals f of x if either the limit of f of x as x approaches infinity is equal to L, or the limit of f of x as x approaches negative infinity is equal to L. So here we have an example of a horizontal asymptote. So here is the natural exponential function, and the line y equals 0 is a horizontal asymptote of this function because the limit of e to the x as x approaches negative infinity is equal to 0. So what we see is that the function will approach y equals 0 as we make x to be a very large negative number. Now we have that the limit of e to the x as x approaches infinity is equal to infinity, since e to a very large positive number is a very large positive number. So we see that as x increases in the positive direction, the exponential function will also increase, and there is no upper bound to the function. Now the next theorem will allow us to determine the limits of certain power functions. So if r is a positive rational number, then the limit of 1 over x to the r is, as x goes to infinity, is equal to 0. Similarly, if r is a positive rational number such that x to the r is defined for all of x, then the limit of 1 over x to the r as x goes to negative infinity will also be equal to 0. So this will be useful for us when we want to determine the limits to infinity. Now we use the notation the limit of f of x as x goes to infinity equals infinity to indicate that the values of the function become large as x becomes large. So now let's have a look at some examples of calculating limits at infinity. So for the first example, we have the limit of 3x minus 2 over 2x plus 1 as x goes to infinity. So one method that we can use when we're working with rational functions is to look for the highest power in the denominator. So here in the denominator we have 2x plus 1, and the highest power of x is x. And so to deal with rational functions, we're going to divide every term by the highest power of x in the denominator. So since our highest power of x in the denominator is x, what we will do is divide every single term by x. So in the numerator we have a 3x over x minus 2 divided by x all over 2x over x plus 1 divided by x. So after we divide every term by x, let's simplify all of the fractions. So 3x over x, symbol simplified to 3. Then we have minus 2 divided by x. And in the denominator, we have 2x over x, which will simplify to 2. And then we have plus 1 over x. So now that we have simplified our limit, we can now look at taking the limit of x going to infinity. So what happens if we let x go to infinity? Well, 2 over x, as x approaches infinity, will go to a very small number. So if you imagine x as being a very large positive number, then if I take 2 and divide by a very large number, then this will go to 0. Similarly, if we take 1 and divide it by x, as x goes to a very large positive number, then 1 over x will also go to 0. So as x goes to infinity, 2 over x will go towards 0. And the same thing happens with 1 over x. And this is due to our theorem that we discussed earlier. So now, we can now simplify our limit. So we have 3 minus 0 divided by 2 plus 0, which is 3 over 2. And so the limit as x approaches infinity will go to 3 over 2. And because our limit goes to a finite number, this tells us that the line y equals 3 over 2 is a horizontal asymptote. So here's the graph of 3x minus 2 over 2x plus 1. So we see that as x gets a very large positive number, then the function will approach 3 over 2. And so the line y equals 3 over 2 is a horizontal asymptote of this function. So let's have a look at the next example. We have the limit of x minus 2 over x squared plus 1 as x approaches negative infinity. So again, we're dealing with a rational function. And so the method is to divide every term by the highest power of x in the denominator. So the highest power of x in the denominator is x squared. And so we're going to divide every term by x squared. So now let's simplify our limit. So x over x squared simplifies to 1 over x. We have minus 2 over x squared all over x squared over x squared simplifies to 1. Then we have plus 1 over x squared. So now let's take the limit as x approaches negative infinity. So what happens to 1 over x as x goes to a very large negative number? Well, if we look at our theorem, we know that this will go towards 0. Similarly, we have 2 over x squared, and this will also go towards 0. And 1 over x squared, as x goes to negative infinity, will also go to 0. And so we have 0 minus 0 divided by 1 plus 0, which is 0 over 1, which is equal to 0. So the limit as x approaches negative infinity is equal to 0. And because the limit goes to a finite number, then this tells us that the line y equals 0 is a horizontal asymptote for this function. So here's the graph of the function x minus 2 over x squared plus 1. So we see that as x goes to a very large negative number, then the function will approach the line y equals 0, or the x-axis. And so the line y equals 0 is a horizontal asymptote of this function. So now let's have a look at the second exercise. Let's find the horizontal asymptotes for the given function. So for the first example, we have x over x squared minus 9. So let's determine if this function has any horizontal asymptotes by using limits. So here we want to check the limit as x approaches infinity and as x approaches negative infinity. Now for this function, we can actually perform both of the calculations at once because the methods for calculating the limits to infinity or limits to negative infinity are identical. So we can write the limit as x approaches plus or minus infinity. So again, we want to look for the highest power in the denominator. And in this case, the highest power is x squared. So we will divide every term by x squared. So now let's simplify. We have the limit as x approaches plus or minus infinity of 1 over x divided by 1 plus 9 over x squared. So now let's take the limit. So let's let x be a very large positive or negative number. And as x gets very large, either in the positive or negative direction, 1 over x and 9 over x squared will both go to 0. So then this will give us 0 divided by 1 plus 0, which is 0. And so this tells us that the line y equals 0 is a horizontal asymptote. So here's the graph of x over x squared minus 9. We see that as x goes to a very large negative number, the function approaches 0. And as x approaches a very large positive number, then the function will also go towards 0. So the line y equals 0 is a horizontal asymptote in both the negative and positive direction. In the next example, we have f of x is equal to the absolute value of x divided by 3x. So for this function, we will need to look at calculating the limits separately, because depending on the sign of x, the function f of x will change. So let's have a look at the limit as x approaches infinity. And let's remind ourselves what the absolute value function of x is, given as a piecewise defined function. So it's equal to x if x is greater than or equal to 0, and it's negative x if x is less than 0. So if we're letting x go towards positive infinity, then the absolute value of x will be equal to x. And so we have the limit as x approaches infinity of x divided by 3x. And here we can simplify our limit, so we can cancel the factors of x. And so we end up with the limit as x goes to infinity of 1 over 3. And if we take the limit as x goes to infinity, that gives us 1 over 3. So that tells us that the line y equals 1/3 is a horizontal asymptote. So now let's also calculate the limit as x approaches negative infinity. So now what is the absolute value of x if x is a very large negative number? Well, the absolute value of x will be equal to negative x. So we have negative x divided by 3x. And so we can simplify this limit by canceling the factors of x. And so we have the limit as x approaches negative infinity of negative 1 over 3. And if we take the limit, we get negative 1 over 3. And so this tells us that the line y equals negative 1 over 3 is a horizontal asymptote. So here's the graph of the absolute value of x over 3x, and we determined that as x goes to positive infinity, then the function will go towards 1 over 3. So 1 over 3 is going to be a horizontal asymptote for large values of x in the positive direction. And if we let x go to negative infinity, then we found that the function goes towards negative 1/3. So for very large negative values of x, the function will approach negative 1 over 3. So the line y equals negative 1 over 3 is a horizontal asymptote. So in the third example, we have f of x is x squared plus x all over 3 minus x. So we can calculate the limits to plus and minus infinity. Since we're dealing with this rational function, we can do both calculations at the same time. So let's approach plus or minus infinity. And here the highest power of x in the denominator is x. So we're going to divide every term by x. So we have x squared over x plus x over x divided by 3 over x minus x over x. So we have the limit as x goes to plus or minus infinity of x plus 1 divided by 3 over x minus 1. So now let's let x go to plus or minus infinity. We know that 3 over x will go towards 0. And so we have, in the numerator, we have plus or minus infinity. And so plus or minus infinity plus 1 is still plus or minus infinity. So the numerator goes to either a large positive or negative number. In the denominator, we have 0 minus 1. And so we have plus or minus infinity over negative 1, which gives us negative or plus infinity. And so what this means is that as x goes to positive infinity, the function will go towards negative infinity. So it will go to a very large negative number. And as x goes to negative infinity, then our function goes to positive infinity. So it goes to a very large positive number. Since the limits do not go to a finite number, then this tells us that there are no horizontal asymptotes for this function. Now for the last example, we have f of x is 1 plus x squared divided by x squared minus x to the fourth. So let's calculate the limits to plus or minus infinity. So here, the highest power of x in the denominator is x to the 4. So we're going to divide every term by x to the power of 4. So that's 1 over x to the 4 plus x squared over x to the 4 all over x squared over x to the 4 minus x to the 4 over x to the 4. So let's simplify. We have the limit as x goes to plus or minus infinity of 1 over x to the 4 plus 1 over x squared divided by 1 over x squared minus 1. And now we will take the limit as x approaches plus or minus infinity. 1 over x to the 4 will go towards 0. Same with 1 over x squared, as well as this 1 over x squared. So what we have is 0 plus 0 divided by 0 minus 1, which gives us 0. And since the limit goes to a finite number, we can conclude that the line y equals 0 is a horizontal asymptote. And it will be a horizontal asymptote in both the positive and negative direction.